All right. So today, we get to our notes. That's my list. So on Wednesday, last time we met, we talked about redox equations, and what I'm going to do for in that recitation video, there's actually an error in the last problem, but I have some call outs in the video to like bring it to your attention and make sure that you understand like what happened and how to fix it or how I fixed it. So I actually showed that because one of the redox equations, when I was solving it, balancing part of it, I left off a coefficient, and you'll see that. But I don't want you to like get freaked out about it when you see it because I did put the correction in there. So but that's already posted. I just need to send you the link to it. So we talked about the balancing redox equations. Now we're going to move to the next topic, which is dealing with stoichiometry. So let me slide this down some. And I'm going to introduce stoichiometry using this diagram just to talk about what it is. it's a term that sounds like complicated, but it's really not. And what we learned in the past is that if you have a relationship between two things or even three things or however many things, you can solve for any one of those things. All you need is a way to convert from one to the other. And so that's what stoichiometry is for us. Excuse me. So today is the April Fool's Day. And we're going to be talking about stoichiometry. And while we're talking about this, what you're going to realize is that this is nothing new. This is not some, rocket science. This is all stuff we already know. We've dealt with moles, we've dealt with grams, we've dealt with molarity, we've dealt with density, we've dealt with all these things and how to convert in between them, molecules to moles, so on and so forth. We've done all of that already. We have a way to do each one of those things. And so what we're going to do is kind of tie all of it together under the umbrella of stoichiometry. Right. So what stoichiometry is literally studying what we call the quantitative relationships. So quantitative relationships between the substances and a reaction. All right, 1 second. All right. So what does this actually mean? Quantitative relationships between the substances and the reaction. Well, we've been talking up to this point a lot about balancing equations and about figuring out like how to balance equations so that they're the same number of atoms on each side. So because that's the law of conservation of matter, right? You can't make matter or destroy matter. It's always equal. It just makes change forms, all right, or change states. So this diagram here is basically I'm gonna use this to kind of explain how all this stuff ties together. So here, let's say we have moles of A. right? We got moles of A. If we know the number of moles of any given substance, we can convert it into mass, right? Using molar mass, which is, if you remember, grams per mole, right? If we know grams per mole, we can multiply moles times molar mass to get the mass in grams, right? If we know the mass, we can get the volume. Because there's a relationship between mass and volume and density, right? This is density is mass over volume, right? So we know that if we got moles and we got the molar mass, we can get the mass. If we have mass and the volume, we can get, or mass and density, we can get volume. And even the mass, volume, and density relationship can be manipulated. We've seen that already. If you have moles and a molarity, that relationship can also give you volume, because molarity is moles per liter, right? Or moles over liters. That's the units for molarity. We studied that already. If you have moles and you want to get particles, wrong pen, particles, right? Particles being atoms, molecules, whatever. You can figure that out using Avogadro's number, right? Which is 6.02 times 10 to the 23rd particles per mole, right? So if you know moles, you can get particles. Just multiply moles times Avogadro's number. The moles are going to cancel, and you'll be left with whatever particle you're looking for, whether it's atoms, whether it's molecules, whether it's whatever, slices of pizza, basketballs, it doesn't matter, right? But the other part of this is that you can also go between moles of one substance and moles of another in a specific reaction using what we call the stoichiometric factor. All this is a fancy term. All it means literally is the ratio. I'm gonna put this in a different color. It's the ratio. So in a given reaction of, let's say A, B, let me just show it down here. So you got a sample reaction. If you have A plus B going to two different compounds, C plus D, like a double displacement. And let's just say, for the sake of argument, that to balance this is 3 Bs, and that gives us right 3 Ds. Just for the sake of argument, it's a generic example. All right, what that stoichiometric relationship is, or the factor is, let's say if I want to compare B to D, then the ratio is 3 moles of B will be equal to 3 moles, or the relationship of D, right? So if I want to write that as a ratio, it would be 3 moles B over 3 moles of D. But none of this is possible unless we know the coefficients. And that's where balancing comes in, because without the coefficients in an unbalanced equation, no matter what kind of calculation you try to do, it's not going to come out right, because the coefficients have to be right, right? So the coefficients are the key to converting between the different substances in a given reaction. So I'm going to write that down here. So coefficients from a balanced reaction. This is the key right here. It's got to be balanced. If it's not balanced, nothing that you do is going to be right. So you gotta have it balanced first before you do anything else. Right. So the coefficients from a balanced reaction are the key to converting between substances. So if I want to go from A to B, I need to know what the ratio is of A to B so I can convert A into B. And vice versa. If I want to go from B back to A, I need to know what the ratio is. So I need to know how to set this up. And we're going to talk about this in more detail with some more specific examples. All right. So let me give you another example, of a less generic example, but not necessarily the one that we're going to use to display all of our skills. All right. But let's just say, for instance, you have N2 plus H2, and I'm using that to make NH3. All right. Is that balanced? That answer should have came out so fast. It should have broke the speakers on the computer. Everybody should have answered that question. Right? This reaction is not balanced.
No.
Mm-mm. 3 hydrogens on the left, 2 on the right, 1 nitrogen on the. I'm sorry, 3 hydrogens on the right, product side, 2 on the left, 1 nitrogen on the right, and 2 on the left. All right. How will we balance it? Let's balance it. So let's do this. So we got 2 N's, we got 2 H's on this side, we got 1 N and 3 H's on that side. How would you balance it? What do you want to balance first? Nitrogen or hydrogen?
Wouldn't for hydrogen, wouldn't you put a big 3 behind it and then just put a 2 behind the NH, so that would be
So a 2,
entire,
you want to put a 2 here?
yeah, for the coefficient for the entire
Right there?
equation. Yeah.
And then you want to put a 3 here?
Yeah.
All right, so let's see what we got. So the nitrogen, it stays the same, but the hydrogen, we're going to say that's times 3. So that'll be 6 hydrogens on this side. Over here, this is times 2. So that's 2 nitrogen. This is times 2. So that's 6. So now we see everything is balanced. So we got 2 nitrogens and 6 hydrogens on both sides. That's exactly right. Now let's think about this in terms of this stoichiometry. All that's asking is what the relationship or the ratio is between the different substances. So if I ask you what the ratio of nitrogen gas, which is N2, and this is ammonia, by the way, in case you hear me say it, but right? What if I ask you what the ratio was between N2 and ammonia? What would you say?
Wouldn't it be like 1 to 1?
Okay,
Or
look at the coefficient here. It's understood to be 1.
so it's 1 to
Coefficient here is 2. Go ahead.
So it's 1 to 2 then for the
It's 1 to
coefficient?
2. Yes, so
Okay.
that's what we're comparing. So N2 to NH3, the ratio is 1 to 2. Right? This is what we call a stoichiometric ratio. All right. When you hear that term, that's what it's referring to. What are the coefficients in the balanced equation for whatever 2 substances you're comparing? What about if I ask you the relationship between N2 and H2? What's the ratio there?
1 to 3, right?
1 to 3. What about H2 to NH3? What's that ratio?
It'd be 3 to 2.
3 to 2. That's it. So when we're talking about stoichiometry, what we're comparing are the ratios of the substances in a given reaction. All right, so I'm gonna write that over here in a different color. That's why we call it a quantitative relationship, because we're looking at the relative quantities of each substance in that reaction. I'll fix that later. All right, so it compares the ratios of substances in different reactions or in a given reaction. And you can only use the ratios in the reaction that's depicted, right? You're not going to compare H2 here to H2 in a different reaction. It's always what's depicted in front of us. All right. So let's push this a little further. If let's say, because this is another way that we use stoichiometry, and we use it to predict the amount of product that's going to be. So let's see how we can do that. Predict product formation using stoichiometry. So the way we do that is a stoichiometric ratio. It's like a conversion factor. Just like when we converted grams into moles, like we converted grams into milligrams, we converted liters into grams using density. It's a stoichiometric ratio is nothing more than a conversion factor. So let's say I had 10 moles of, let's say 15 moles of H2 gas. And I want to know how much NH3 I produce. And this is not random, right? We have a reaction right here, right in front of us. All we need to do is figure out what the ratio is of NH3 to H2. And then we're going to take what we have and find what we need, right? So what is the ratio of NH3 to H2 based on the reaction that's given?
2 to 3.
2 to 3. All right. So the way we set this up is going to be standard. It's going to be the same way every time you do it. You take the moles of what you have, because we want moles of what we have. We want to use it to find the moles of what we're looking for. So 15 moles of H2. In the bottom of that ratio, I'm going to put H2 because that's what I want to cancel. So the ratio is 3 moles of H2 for 2 moles of NH3. So let's use that as our conversion factor. So this is 3 moles. And then in the top, right? And if you remember when we did conversion factors, it was always the top number being what we wanted and the bottom number being what we want to get rid of, right? So it's this number of moles times this conversion factor. This is this stoichiometric factor. Right, and that's derived from the balanced equation. All right, so what's the answer to that? Let me see, 15 times 2 divided by 3. In that, when they give me 10 moles?
That's what I got, sir. Yes.
All right, 10 moles of NH3. Perfect. All right, we could take this further. If we know the number of moles of NH3, we could also figure out how many grams that is, right? How do we go from moles to grams? What if I ask you how many grams are produced instead of moles, right? You can't go from moles to grams directly from moles of H2 but you can go from moles to moles and then moles to grams. How would we do that?
Molar mass.
Good. So if I wanted to find out the number of grams, keep picking the wrong pen. Right, that's moles times molar mass. We learned that relationship early on. So all we need now is 10, the moles here, which is 10 moles, times the molar mass of ammonia. How do we get that if we don't know it? If you don't know the molar
Repeat
mass,
that one more time.
how can we get molar mass if we don't know it? Is there a way to derive it? Yeah, we spent a considerable amount of time discussing about a week ago.
It's weight over grams, if I remember correctly. Not weight over grams, but weight of like the entire of both elements.
Yeah. So all the atoms added together, right? So
Yeah.
nitrogen is 14, hydrogen is 1. I'm rounding those up way up based on their atomic masses. So this will be what, 17 grams per mole. That's the atomic mass of ammonia. So 10 times 17 grams per mole, right? What would that give me? 170 grams. So all those little relationships we learned early, now we're going to apply them to other reactions and to a real scenario, right? All right. So when you look here, again, we need a balanced equation. With a balanced equation, we can figure out anything. Even if we're given grams to start with, we can figure out moles. If we're given moles to start with, we can figure out grams. If we're given liters to start with, we can figure out moles as long as we have a concentration or some way to go between units. We're good. All right, so let's look at another equation. And I'm gonna write it out first, and then we're gonna balance it, and then we're gonna go through and answer some questions about it. All right, so let's say we have, change colors. Let's say we have calcium hydroxide. All right, and that's gonna be plus phosphoric acid. And that's gonna give us calcium phosphate. Plus water. All right, and this is an example of an acid-base reaction. Phosphoric acid is your acid. Calcium hydroxide is your base. And then you get on the other side, this is acid, this is base. Other side, you get a salt plus water. All right. So now we need to balance that. So this morning when we balanced this, I kind of gave the class a little bit of a cheat, depending on, and this is case by case, but depending on what the ions are, right? You know, before we talked about this already, how we can keep those polyatomics together if they're present. We already know that cheat. So PO4 is a polyatomic that we can keep together because it's intact on both sides. So we don't have to break that up into its elements in order to balance it. But another thing that we can keep together, we can say this is OH. And over here, when we look at water, we can consider water as this. So this is H, OH, like that. All right. Anybody not following that, or did that throw anybody off? I don't want to throw you off. I want us to all be on the same page. So we'll keep that together. We're gonna keep that together. All right. So let's do our inventory and see if we can balance this thing. So we got 1 calcium. We got 1 OH. All right, we got 3 hydrogens. We have 1 PO4. All right. And then on this side, what do we have? How many calciums?
3.
3 calciums. We have 1 H. We have 1 OH. And we have 1 PO4. Everybody okay with that? All right. What do you want to balance? Actually, I screwed that up. This is 2 OHs. I forgot that little subscript out there. All right. So we got 2 OHs, 1 calcium, 3 H's, and 1 PO4. And then over here, 3 calciums, 2 PO4s. I screwed that up. Come on, Russell. And then 1 H and 1 OH. What do you want to balance first? We can pick any one of those atoms we can balance first, and we'll deal with the rest of them as they come.
You can put a 3 behind the calcium.
Okay. So let's do that. Let's put a 3 here. All right. So that's going to be this times 3. So that's going to be 3 calciums. That's going to be OH also times 3. And that's going to be affected by that subscript. So that's going to be 2 times 3, which will be 6 OHs now. All right. And we haven't touched H's. We haven't touched phosphorus. So now let's see what we got. So if that's the case, now we can go ahead and balance OH. Right? How we balance OH if this is the source of OH right here? What would you do? If we only got 1 on this side, right?
Put the 6 over there.
Let's do that. Let's put a 6 here. And that's also going to touch the hydrogens. So that's going to be, let me change the color so they all match. So that's a 6 here. So that'll be this times 6, which is 6. That'll be OH times 6, which is 6. Following? Everybody good? So right now we have the OH is balanced. The H's are not. The calciums are. The PO4s are not. But we can balance both the H's and the PO4s at the same time because they're together in the same molecule. So what do we need to balance out the hydrogens and the phosphate anions? What would you do?
Put a 2.
We put a 2 right here. And that'll bring us home. Right? So that's going to take this up to 6. Take that up to 2. And now everything is balanced. Right? So now we got the coefficients that we need. This is why balancing is so important. If you don't balance the equation, when we get ready to answer questions about the stoichiometry, they're all going to be wrong. So we need to be able to balance these equations so that we can answer the stoichiometric questions as they come. So now here's the question. Right? I want to know how many moles of calcium hydroxide will it take to react with 1.36 moles of phosphoric acid? So I'm going to write that out. So this is calcium hydroxide. Will it take to react with 1.36 moles of phosphoric acid? Right, that's the question. So what we're looking for is this. That's our desired right? That's what we're looking for. What we have is this. All right. What we need is a way to go from what we have to what we desire, right? We need a conversion. And so based on the balanced equation, that's how we can do that. So what is the ratio between phosphoric acid and calcium hydroxide? Based on the coefficients that are there.
3-2, right?
3-2. Good. So this is my ratio. 3 moles to 2. I'll write it in later. And that's all based on that balanced equation. So if I wanted to convert phosphoric acid into calcium hydroxide, not convert it chemically, but relationally, like to figure out how many moles of calcium hydroxide would be the same as 1.36 moles of phosphoric acid. And I use these two numbers as my ratio. Which number would I put in the top of the ratio?
Since you're looking for calcium, you'd put the 2 on the top because you want the
Okay.
calcium to cancel out.
No, I don't. I want the acid to cancel out.
Oh, okay. So you
Because
put
look,
it at the bottom then.
right. You see right here, this is what I want. Right here, this is my desired outcome, and this is what I have. So anytime you're setting up a ratio, you put what you have on the bottom, what you want in the top, so you can cancel out what you already have, and then convert it into what you want. So we're gonna put this number in the top: 2 moles H3PO4, 3 moles calcium hydroxide in the bottom. Oh, I did exactly what I just said not to do. We want 3 moles of calcium hydroxide in the top, my bad. And 2 moles of H3PO4 in the bottom. That's my ratio. That's my stoichiometric ratio. And we're going to take that and multiply it times 1.36 moles of phosphoric acid. Right? So this is going to cancel moles of phosphoric acid. And I'm left with this number for, so I'm left with this number right here, which I can easily calculate. All right, this is a very simple calculation. So it'll be 3 times 1.36 divided by 2. And that should give me 2.04 moles of calcium hydroxide. Anybody else get that? 2.04? All right, so it's just 3 times 1.36 divided by 2. All right, so I got 2.04 moles of calcium hydroxide. What if I ask you how many grams of calcium hydroxide would I need? Can we go from here to grams?
Yes, if we use molar mass.
So you need molar mass to go from moles to grams. Can somebody Google that, molar mass of calcium hydroxide? You can Google it, or you can go ahead and add it up from the periodic table. I can't remember calcium. I think it's 40 something. 40.
Calcium is 40.
Okay. Oxygen is 16. Hydrogen is 1. But since there's a 2 out there, there's going to be 32 and 2. So that's 34 and 40. What is that? 77 grams per mole? Something like that.
I got 74.
74.
Yeah, I
Yeah.
might.
You're right. Right. 7,
Okay.
because it's 17 times 2 is 34. Yeah, that's right.
Okay.
74 grams per mole. My bad. All right. So can I now convert moles into grams? I just take 2.04 moles times what? 74 grams per mole. Moles are going to cancel, and I'm left with, what is that? About
I got
140,
150.
150.
Yeah, 150.96.
All right, 0.96 grams. Right. So the way this works in real life is, if you think about, if you're running this experiment in a lab, and I told you that you needed to start with 1.36 moles of phosphoric acid, and I told you to figure out how much calcium hydroxide you need to use all of that up. This is how you would do it. You would balance the equation, take the ratio, and convert phosphoric acid moles into calcium hydroxide moles, and then figure out how much you need to weigh out in order to use up all of the phosphoric acid. All right, that's how that works. All right. Let me ask this question, because we can push this a little further and say, how many moles of product will we get? Let's ask that. Any questions before we do this other part? Again, none of this is new. The only thing that's new, relatively new, is the balancing. But all the conversions, all that we've done already. We just converted different stuff, but it's the same concept. What you want in the top, what you want to get rid of in the bottom, and you multiply that by what you have. It's that simple. All right. Let's ask this question, push this a little further. How much? Come on now. How much calcium phosphate will I said gram, my bad. We're still working with the same example. 1.36 moles of phosphoric acid produce. All right, what do we need from that equation in order to figure this out? If this is my balanced equation, now I want to know how much product, how much calcium phosphate I'm going to get from phosphoric acid. What's the ratio between them?
You said calcium and phosphoric, right?
Calcium phosphate. It's on the other side, the product side.
Oh, okay. That's not 3 to 2, right? Because you said calcium phosphate, so just that one equation. What are
Yeah,
we?
it's this one over here.
Okay, and then what's the other one that we're doing the ratio with?
Here. So we want
That
to
one.
know. Yeah,
So
we
that's
still
like
go ahead.
that's 2 to 1, ain't it?
It's 2 to 1. We're still using phosphoric acid, but I'm extending the question to say how much product will it give us? We know how much calcium hydroxide we need to react with it, but now I'm asking how much product is it going to produce? And so the way we answer that is to take that ratio, 2 moles of phosphoric acid to 1 mole of calcium phosphate, because the coefficient here is understood to be 1, right? So we're going to set that up down here. And we want to get rid of phosphoric acid. So I'm going to put that on the bottom. So 1 mole of calcium phosphate over 2 moles of H3PO4 times 1.36 moles of H3PO4. And we're going to solve this by canceling those out. All right. So that's what would that be? 0.068 or 0.68. Is that right?
Yes, sir. I got 0.68.
So 0.68 moles. So what that means is that when I react calcium hydroxide and phosphoric acid, and I use 1.36 moles of phosphoric acid, that's going to produce 0.68 moles of calcium phosphate. That's what that means. All right. I think we got time for one more question, one more example. So let's do this example real quick, and then we'll be done for the day, and you can go and enjoy your weekend. All right. Let's do one more example. So here's the equation. We got ammonium sulfate plus excuse me, calcium hydroxide, and that's too big. That's gonna give me ammonia plus calcium sulfate plus water. All right, this is not balanced, by the way. So let's balance it. So over here, I'm going to keep the sulfate intact because it's the same on both sides. I'm also going to do the same little trick I did earlier with water, right? So I have an OH over here, and then I have over here H, OH. So I'm going to keep that, I'm going to separate that like that because water is nothing more than H plus, which is a proton, and OH minus. So let's do that. All right, so we'll do our inventory over here. We got nitrogen, hydrogen, we got SO4, we got calcium, and then we got OH. On this side, same atoms, just in a different arrangement. So we have nitrogen, we have hydrogen, we have SO4, we have calcium, and we have OH. Same atoms, different arrangement because a chemical change took place. All right, so how many nitrogens do I have on the reactant side? By the way, just as a refresher, left side of the arrow, always reactants. Right side of the arrow is always products. So how many nitrogens do I have?
2 on the left side.
Okay, good. And I have 8 hydrogens. Is that right? Because I'm separating OH and H. So the H with the OH I'm not counting because it's already going to be counted here. So I have 2 OHs. I have 1 calcium and I have 1 SO4. Remember, if you see that polyatomic, like a sulfate, a phosphate, a nitrate, anything like that, if you see it intact on the other side, balance it whole. Don't break it apart because that's going to make the process more laborious if you break it apart. All right, over here, 1 nitrogen, 4 hydrogens because of this one and these 3 right here, 1 SO4, 1 calcium, and 1 OH. All right, what do you want to balance first? Let's start out with the OHs. Let's start with the OHs. So let's do this. Let's put a 2 here in front of water. And that's going to make this times 2. So we'll have 2 OHs. It's also going to increase this number. So instead of 4, now it's going to be 3 plus 2, because you got 2 here and then 3 here. So that's going to be a total of 5 hydrogens. Is that right?
Yes.
Okay. All right. So now let's see about balancing the hydrogen, because we got 8 on the other side. Actually, let's balance the nitrogens, because if you look right here, you can see that this NH3, when you balance the N, it's also going to affect the H, and it's probably going to bring us into balance altogether. So what would you do to balance the nitrogens, since we have 2 on the other side?
Put a 2 on the reactant side, or not the reactant, but the product side.
Yeah, because on the reactant side, you have 2, right? So if I do that, there's going to be what? 2 nitrogens. And then this number now is going to go up. It was 5. Let me put this over here. But now I'm just going to manipulate what's in here already. That 3 is now going to become a 6. Right? Because this number now is going to distribute to here. So it's 2 times 3. So now that'll be 6 hydrogens there, and then 2 here. So that'll give me a total of 8 hydrogens on that side now. Right? And it looks like we're good to go. So this is, that's 2, that's 2, that's 8, that's 8, 1 SO4, 1 calcium, 2 hydroxides. Everybody clear on that? How I got the 8 hydrogens? That didn't go over anyone's head, did it?
Yes, sir. We got
Yes,
it.
sir.
All right, cool. All right. So now that's that. So it's balanced. So now here's the question. Give me 2 more minutes of your time, and then we'll be done. How many? 2 minutes and 5 seconds, because I had the wrong pen chosen. So how many NH3 molecules, not moles, are produced from 7 moles of ammonium sulfate? How do we set that up? Because if we start with 7 moles of ammonium sulfate, which is one of the reactants, how much NH3?
Hey, howdy. Hmm? No,
All right. How do, oh Lord, it's Friday. I'm gonna chill. How do we set that up? Based on the balanced equation that we just did. What are we looking for?
The ratio between ammonia and ammonia sulfate.
Exactly. And we want the ammonia to be in the top and ammonium sulfate to be in the bottom, because that's what we have. And then ammonia is what we need. So the ratio is 2 to 1. So it's 2 moles of ammonia and 1 mole of ammonium sulfate times 7 moles of ammonium sulfate. I'm just going to put AS. I don't feel like I'm going to run out of room. So this is going to cancel. What is that?
14.
14 moles of NH. 3. But notice it didn't ask for moles. It asked for molecules. How do we go from moles to molecules?
Molar mass.
Molecule, not in this case. A molecule is a particle, right? So we
Okay.
got a way for doing that right here. Anytime we want molecules, atoms, particles, we always use Avogadro's number. So it's going to be that number, 14 moles, because Avogadro's number is per mole, is going to be 14 moles times 6.02 times 10 to the 23rd. It asks for molecules, so we'll put that in the top. Molecules per mole, right? Moles will cancel, and then we'll end up with molecules. But you can calculate that on your own. All right, I'm 5 minutes over, so I apologize for that. All right, so what I'm gonna do, I'm gonna post this to YouTube. I'll send you a link, and I'll also post the recitation video, send you a link to that. And the handout for the recitation video is already posted to Blackboard. All right. Any questions? Everybody good?
Yes, sir.
Next exam is going to be posted today, and it'll be due on Sunday. All right.